And we're coming back to Slovakia, we're coming back to Košice with the last presentation today. And it's going to be delivered by an expert in the field of implementing artificial intelligence in manufacturing and non-manufacturing processes. He serves as the head of the digital team at US Steel Košice with the topic AI-driven innovations in real-time prediction of steel converter blowing parameters. Please welcome Robert Vandlík.
Good afternoon. Thank you for introduction. Thank you for opportunity to be here. My topic is probably a bit different than the rest of the topics here, but I'll try to be practical, and considering that this is the last presentation for today, I'll try to be also efficient and deliver the message quickly and efficiently. So many of you are locals and probably know what is US Steel. And does this thing work? Yes. Many of you know that there is a steel, and many of you also know how it's being used. So everybody can imagine it's automotive, and the cars are built of steel, and also the appliances. Some can even know that it's packaging, and cans are made of steel, and there are motors, and there is construction steel. There is a lot of steel around us, and a lot of products built from steel. But many of you don't know what are the shapes and what is the word behind word steel. So it's not one product, but it's a big portfolio of products, and it's important for you to understand later on in the presentation. But we have several form factors, let's call it, of the steel. So it's slabs, it's big chunk of steel, pretty heavy, pretty big, substantial. Then it's rolled into the coils, so think of parenica, the big roll of steel, and then you can cut it into the sheets. So this is how the mechanically, or how are the shapes of this. And then there are different families or grades or whatever we call it. So for the packaging, we use thin steel. So that's a completely different steel than for electrical, that is used for electric motors. Then it's color-coated, that could be used for the roofs or galvanized for cars. So there is a huge world of steel and steel products and everything. So it's a very diverse product. With this in mind, also the plant that is manufacturing this, it's pretty broad and pretty big and substantial. So think of, I think it's 2,000 football pitches, so it's pretty big, 10 square kilometers. And it's processing around 8 million tons of materials, raw materials, into 4 million tons of steel. So if you can imagine the pile of this, it's pretty substantial, but it's not very uniform. So you have 8 division plants that have a completely different inputs and outputs. So it's like 8 different plants within one huge plant. And this is interconnected with a huge railway. We have 300 kilometers of railway, and the different processes that some are really close to absolute zero, so very, very, very cold when you're making your oxygen, or it could be 1700 degrees for the melted iron, so pretty big difference in that. And some processes are very slow, so snail-like, and some are supersonic speed. So pretty broad, pretty big, and a lot of opportunities. Well, that's the takeoff from this slide. I'm not going to talk about this slide much. So this is the production workflow in general. So you can see all these boxes. All these boxes are completely different processes and different things. And this is not even the full thing. So this is only the second portion of it. I didn't put the first one. But for us, the important is, and I hope this is the laser. Yes, it is. We'll be talking about these yellow boxes here. So these are the converters. What is it? So yeah, for the people not involved in steel, it's big. Yeah, it's very big. So it has, with the material inside, it's roughly 180 tons. So it's also heavy, and it's very hot. So the 1700 degrees that I've mentioned before, it's in there, and the most important thing for me and for this project is that I'm going to talk about is you cannot see inside. So the purpose of this thing is basically take an iron from the blast furnace that is not clear, so it has a lot of content from the raw materials, a lot of carbon, sulfurs, what else, and you just blow the oxygen, the pure oxygen through this, and everything burns, and in the end it's pure iron with some leftovers, not much, and this is how you transform from the iron to steel. So there's a difference in iron and steel, between iron and steel, mainly between the purity and the control of the chemical composition of that thing. So here are some pictures so everybody can visualize what it actually is. I'll start from the right bottom. So this is the inside of the converter. So think of big pot, and it's very hot in there. So there are bricks inside, so otherwise it will melt. And top bottom is actually the converter thing. So that pot is the part on the bottom, and the top thing is the hood, so basically mechanism how you capture all the gases and everything coming out of it. On top of that, on the right, there is the filling the converter with the pig iron. So this is the beginning of the process. You don't see it through the process, but the end is basically on the left, the big picture, and this is the removing the slag or leftovers from the steel, and that shiny yellow thing down there, that's the steel. This is the product, semi-finished product that is being used for other production downstream. So really the problem is you've seen the slag on the top of that, so you cannot really see during the process inside. You cannot measure the temperature. Ooh, something else here. So what does this mean? You cannot measure the temperature, which is substantial for this process. You want to end at a certain temperature so you can process this downstream. And you also want to control the chemical composition, mainly carbon, because if you blow the oxygen, the carbon is burning, is heating up the thing. And once it burns out, then you have a problem. You have it probably too hot, and you probably have to add it later on in the process. So you burn it, pay for it, and then you add it and pay for it again. Not good. Try to avoid that. And maybe if I go back, you can see the x-axis is actually, the center of that is actually the target for the carbon, the same for the y-axis, but this is the temperature. And you try to have everything within that green square that is in there. This is the optimal, so we've hit the carbon, we've hit the temperature, we are perfect. But you can see on the picture we are a bit off-center. What it means, we are burning way too much carbon from that, so we have to add it later on in the process. And you can see also it's going a little bit up from the optimum, so it's also hot. So you have to cool it down, another energy spent in a useless way. And also it's eating the bricks that are inside the converter, not good as well. So you try to be in that middle. And the problem, if you quantify it, is that only 14% of all the heats, and we do like 80 heats a day. And in the middle, so it's cent to cent, but generally we are losing a lot of money there. So we now know what's the problem. We know what we wanted to build, so we build a model. That model is our AI model. That model is living in certain environment. I'll talk about it a little bit later. But as this is a process that is very hot, very heavy, and basically it can explode, you want to have the user or the operator in the loop as well, because if something goes wrong, he has to make a right call, not to burn everything or blow everything. And if everything goes right, then we achieve the benefit, right? That benefit is what is driving this project, as usual with the corporations. So back to the converter. So you can see very simplified way what it is. So you see the oxygen lines. This is basically a pipe that is feeding the pure 100% O2 down that pipe, and it's very close to the surface of the steel or iron, and it's going there, it's burning, and on top you form a slag. So basically this is what's in there. As I mentioned, you feed the process, or the inputs to this process are pretty clear. It's the pig iron, so basically a pig iron or iron, unclear iron that is coming from the blast furnaces. Then it's a scrap. So roughly 20% of the steel is being recycled. So if you throw away to the garbage with the metals or whatever, you take it to a junkyard, then 20% or that steel is being recycled there. And then you add the oxygen, the element that is helping or is driving the burning of these impurities within. And out of it, you get pretty much only two things. It's the slag, so everything that didn't burn is floating on the top of the steel. And you get the gas, the emissions that you can actually capture and analyze, pretty substantial for the solution of this. So I pretty much mentioned most of this, but really to have a context of this, so we use roughly 7,000 to 8,000 cubic meters per heat of the pure oxygen to do that. So there is 160 tons of steel produced, roughly 7,000 to 8,000 cubic meters of the pure oxygen. We started the temperature 1300, maybe a little bit more, and we get a little bit, it depends on the further processing, but a little bit below 1700 degrees Celsius. So this is pretty much about the process. And the question stands, how do I know what's the temperature inside, and how do I know what is the carbon, right? So I want to hit the dead center of that square that I've showed previously, so how do I know I'm there? Knowing that we have the user in there as well, or we call it operator, so we are building the model. I'll speak a little bit about the data for this model. So this is basically picture before, and this is the end state after. It's not showing the same amount of heats, but you get the picture, right? So we achieved significant improvement. So with 14%, we got, I don't know, maybe 70%. Significantly better, but all the elements that are on this picture need to be in place to contribute to this. So how do you build this model? You can split the data into two distinct categories. So you have static data. We call it static data because it's well known before the heat starts, and it's not changing during the heat, so it's only used to feed the model in the beginning. And these are the obvious things like the weight of the iron that went in, weight of the scrap, type of the scrap, and what's the chemical composition of the iron from the blast furnace. So this is pretty obvious. And then you have the second set of the data we call dynamic data, and this is three main sources of that. One is the exhaust analyzer. So down the pipes from the converter, there is an analyzer that is analyzing the thing. Then we have the oxygen volume, so obviously we know how much oxygen at what speed are we using, and we know also the head position. So maybe you remember from the picture, but on the top of the converter there is a head, and that can move up and down, so we capture more or less the gas. This is important because there could be a composition of the gases that is explosive, so if something goes wrong, you can open it a little bit, add more air, whatever, you control it. So that's also very important. You can see also a little chart and a very little picture of how the dynamic data looks. And also I have a picture that is pretty scary to everybody, but it's showing how the gas capture system is working. It's pretty complicated. So there is the hood. I don't know if you can see it, but then the gas is cooled, it's cleaned because there's a lot of dust and a lot of, I don't know, everything. And when it's cooled and when it's cleaned, then it goes down the pipes, somewhere out to the fan, and then is the actual gas analyzer. What's important for us is that the gas data, so the composition of the gas we are getting, it's roughly 60-90 seconds late compared to the actual process, what is happening. That process overall, the blowing in converter is taking like 15 minutes. 90 seconds may not see as much, but you'll see later on that in the end, it's pretty quick. So these 90 seconds happen, so we have to do something about it. So speaking about dynamic data, this is the typical sample of one heat of the dynamic data that is measured. You can see already from that picture that it's not really straight lines. It goes ups and downs, a lot of ups and downs for all of the data. And if you chart specific signals from that chart and you do it with 10,000 heats, you get a picture like this. So you see the signals that we get from the gas analyzer for different heats could be pretty different. And you can also see that there is some ups and downs, so these are the heats that are restarted. So if you started blowing but the conditions are not right or something is happening, then you stop it, wait, whatever, do what's necessary, and then you restart it. You can see that in this data as well. So this is pretty up and down data, pretty complicated to work with, so you obviously have to do something about it. You don't want to feed all these ups and downs and everything to the model. So basically, you do a signal transformation from all this live data. You do the transformation with the data, and you get the coefficients for these signals. We work roughly with 700 coefficients for these models that you will see later on. And this is the chart that is showing the overall organization of this thing. You have the data that is coming from the level 1 systems, so basically systems that are down there on the converter, and then you have some data from the operator and some from the historical data. And important thing is here that you feed 5 different models. So you have a model, not just one, but you have a model for temperature, for carbon, for phosphorus, sulfur, and oxygen, and you use these models for two distinct use cases. One is the live prediction of the data of the temperature and carbon and these elements, and the other one is the calculator you can use in the beginning of the heat to simulate what would probably happen and what could probably happen if you change this or that. So we use this for two distinct purposes. So now a little bit details about the models. So we have already mentioned two models for each converter. So this is for standard heats and for restarted heats, because the data shows us that there is a big difference between these two. Then each of these models is basically a composed models or composite models built on top of two models. One is linear regression, and this is LASSO, that is capturing the basic physics and chemistry and everything, basic mechanics that is happening inside the converter. And the second one is XGBoost, that is basically taking care of anomalies within the data, so spikes in data, etc., so to be more consistent. Each model is processing roughly 20 static data points in the beginning, and then we have these 10 signals or 10 real-time signals from the analyzer, mainly from the exhaust gas, that are delayed, that we process into roughly 700 inputs. And we have these signals about the volume of the oxygen and head, and then we do everything that we did together. And all for this is that we predict every 3 seconds. Each of the model is making this prediction and making guess what is happening inside. So we have a lot of data for training of these models. So we have data for many, many years, so maybe for 20 years. So it's 100,000 plus hits, so a lot of data to be trained for. But during the training, we found out that historical data from 10, 15 years ago, no more valid. I mean, so much has changed. Within the operations, within the sensors, and how we operate and how we run things doesn't matter. So maybe we use 2 or 3 years to train the models, rest is junk and can go away. We have, and you've seen this in the picture in the beginning, 4 different converters. So now let's do the math. So we have 4 converters. We have 5 elements that we predict. That's 20. And then we have it for started and restarted heats. And then we have correction models. That's the next slide. So there is just to predict what's happening in converters, that's a whole bunch of models that are running and they're predicting things, and all this comes together to visualization that is presented to users that will be shown in a second. Yeah, one more thing, I guess. So even if you do all this work and you have all this static data, you do the analysis and transformation, and you build so many models, we still have a problem. So the models there is some cycle in the models in their imprecision, let's call it. So sometimes the prediction is higher than the actuals, and sometimes it's lower. So on top of these models that you have to build another set of models just to correct this behavior. We try to figure out what is causing it. So we've investigated everything from weather to everything, and we didn't figure it out. So on top of the models, we built the correction models, and the reason was this. So this is the uncorrected model. So you see that it's not in the center of the green square where we want to be. And it's not perfect, I would say. It's a little bit better than we had before, but it's not perfect, and you can see it actually moving during the time. So with the correction models, it's actually much better. So you can have these correction model move the models towards the center, toward more precise or real prescription or prediction, and you see that with this we are much closer to the center that we want it to be. I think this is the desired outcome. So, let's talk about the people. As I mentioned, this is an industrial process, very dangerous in its nature, high pressures, temperatures, and everything. You do not want to cause something bad. So we have the operator in the loop, and you know how is it with the people that work in this for the last 20 years for the same way. It's very difficult to work with these people and explain them why this is better than they've been doing before. Yeah. And the video is not working. Can we somehow click on the play on that beautiful visualization? Who has the mouse? Oh, yeah. Down there. Oh, it's working. So this is the actual gamification or prediction or display that is used for the operators. It's pretty simple. It's a snake-like interface, right? You follow the dots. And once you hit the green thing, green square that is in there, game over, you are successful, right? So you try to hit the edge, and you see that in the last, this is maybe last 30 seconds of the heat blowing, it's moving pretty significantly. There is some delay because some processes has to happen before it stops. But if you can stop it on the corner down left, that's perfect. But everything within the green is quite okay. Yeah, so this is the operator's interface and how we present this data to the operator. Before that, the way they had the data presented is actually on the left, right? So you see all these charts, all this data, and you somehow make the decision when is the right time to stop it. So you try to hit that optimal sweet spot. And before that, when I asked the operators that worked there for 40 years, they had a window to the converter, and they checked the color of the gas, and they knew that it's okay, it's not okay, right? So we've come a long way, and this is the actual interface that they use, and they can pretty much easily understand what is going on. And you see the other dots plotted there, so we can plot also the sulfur and the carbon and not carbon, phosphorus and whatever, and they can actually use that. But I've mentioned it a couple of times. We have the operator in the loop, to really force them, well, that's probably the correct word, but really to persuade them to use the model that it's better statistically that they are, but not right all the time, right? So this is pretty difficult for me to understand that it's when they are once better than the model, then they don't trust the model. They think that the model is wrong, right? And I understand a little bit that their understanding of the world, but statistically we can prove that this is better. But no, yesterday it was way off. I'm doing much better. So we had to build a lot of stuff around it for the operators and for the managers. To really understand what's going on and to really believe that the model is doing better stuff than they're doing. So we've built everyone's favorite KPI, right? So on the top right, that's the pretty simplified manager's KPI where they can see down to the operator, down to the heat, when the button was pressed to stop the heat, and what was the performance of the operator, what was the performance of the model, etc., etc. We are also storing all the data from the heat, so we can actually hit maybe a replay button and replay the heat and model predictions and understand what's happened. And we also display the summary performance data for the model that's available for everybody to see what's the current performance of the model, what's the correction, etc., etc. So a lot of stuff has to be built around it, just to make sure that the humans can understand it a little bit and use it and force them basically to use it. So with that, maybe a little bit about where we want this to go with. I mean, this thing is alive, so we've built it maybe 4 years ago, and it's always something around it. So this is never-ending project in terms, and what we are figuring out that most of these AI projects are never-ending. Everything is changing. The model needs to be changed as well. But during the last couple of years, we've built on the Steelshow where there are many other processes like that, several models. So now we feel it makes sense to start integrating the models together. So model talking to the model. And this should bring additional benefit, and for the human, the benefit will be the lower cost, obviously, and able to simulate what would happen if I run it this way. I use this much different chemistry, I use less oxygen, whatever, based on the current market condition. And there is a whole new world around it. So Steelshow is one of the 8 plants I've mentioned. So we want to integrate this upstream. So also to integrate blast furnace into this and come to the overall cost optimum. I mean, holy grail for corporation. So with that, I think that was the last slide. So I guess questions. Thank you very much.
Thank you. I have one question. Have you watched the converter process yourself? Is it possible for you to go there and watch it, how it works?
Yeah,
so you
once for a few seconds, probably. Yeah? No. When it's happening, it's already close, so you don't see it.
So you can.
But you can feel
cannot,
the heat.
yeah?
It's like staring at the sun. It's pretty hot and substantial.
It's not like that you would understand the process better, right? It's not.
No.
It doesn't work like that.
No.
Okay. We've got 2 questions in Slido. Is it only one AI solution used in US Steel, or you have more of them for different processes too?
Yeah, now I should say, good question. Yeah, we have pretty significant number of those now. So as I mentioned, it's pretty big plant with different processes, and the projects that we do, my team is doing what we would call AI solutions. So we have many projects already deployed within the plant, from the basic manufacturing like this to commercial things to picture recognition and that kind of stuff. So pretty much everything. A lot of opportunities, a lot of different stuff that we already made. Pretty interesting, I would say.
And what are the biggest challenges when introducing AI models, such as the one presented into the production? Maybe the one you mentioned, the talking to people and persuading them.
Yeah, 2 things. Humans, right? So all this AI, this is a statistical thing, right? So I'm sure somebody mentioned today that GPT models could be hallucinating. So these models do hallucinate in their own way as well. So sometimes they are completely wrong, but statistically are better than the humans. So this is first the difficult thing for the humans to digest. And the second thing would be the data, right? So you have so many processes, so much data, but the data quality is usually an issue.
Okay.
So if the data, the experience is if the data was already used for some decision making, that is usually the good quality. But if it's some sensor that was installed 10 years ago and nobody is making decisions based on that, or is not feeding any critical system, then it could have gone haywire 10 years or 5 years ago and nobody knows. And if you feed the model with such data, then it's already a problem. So you have to figure it out, correct it, etc., etc.
Mm-hmm. And are you doing any, regarding the human thing, any maybe like workshops for these people internally that they know what is really happening, why this is important to do nowadays?
Yes. The part of the what we call a digital transformation, I know, corporate buzz. There is also an upskilling effort aimed for various people. So we tried for everybody in the company to understand what is AI. So basically 10 minutes introduction, what it is. And then we try to work with the people that may have potential projects more closely to explain what is the potential. We try to upskill them, so use the digital tools available, play with this, and yeah, you try to upskill them.
And maybe you also persuade some of them to try some new job or position.
Very difficult usually, but yeah. It's changing. I mean, this technology is changing everything, so everybody needs to adapt.
Yeah. One more question popped in right now. Do you use spins? I don't know what is it, but
yeah, that's a good question as well. Yeah, so it's physics-enabled neural networks. Just a second ago we spoke about that we do not have a good quality of the data, and this can cause models to go haywire. So there is a certain type of models that use a blend of physics and chemistry and modeling, so real equations of how things work with combination of machine learning and data. So if there is a problem with the data or something unexpected happens, there are physical and chemical bounds where this model could go and not cause disasters. And also it's improving the model's performance. So yes, we already have one in testing, and I think it's pretty interesting. So it's not all AI, it's not all old way, it's a combination of both that seems to be promising.
I think it's very interesting, all these processes and everything, and also that we've got you here, so you can really be like a proof that also in the industry and manufacture, these processes happen and the digitization works, right? And AI is also used. Thank you very much. That was Robert Wandlik.